So today what we're going to look at is a series that's called an alternating series, and we're going to see the convergence of it using a test called the alternating series test. All right. Up to this point, we've looked at a lot of series, but they've all had positive terms. Okay. So we're going to look at what happens when you have both positive and negative terms. Okay. And when they start alternating, either the odd terms are negative or the even terms are negative. Okay, that's called an alternating series. Okay, so like here, the first term here is positive, second term is negative, third term is positive, fourth term is negative. And so this is considered what we call an alternating series. This one turns out, okay, this is a geometric series and our R is -1/2, okay? So I'm gonna show you another way to write this, okay? This is also equal to sigma and n equals 0. So our initial n value is 0 to infinity of -1 to the n. And then we could rewrite this as 1/2 to the n. So this would be considered an alternating series, and this part of it is a geometric series. Okay, and we are going to call this term right here without the negative to the power, we're going to call that a sub n. All right, so that's how we're going to define what a sub n is. It's going to be the positive part of this. Okay, all right. Okay, so we know that this one, because our R value is between -1 and 1, we know that this one would converge. Okay, all right. And we can just use that by the geometric series. Okay. All right. So how about this one? Let's go to the next part of this test. So we have an alternating series. If n equals 1 to infinity, we have -1 to the n power a sub n. If we write it like this is going to cause our first, third, it's going to cause the odd terms to be negative. Okay. If we write it like this, n equals 1 to infinity of -1 to the n plus 1 power, when we put 1 in here, it's going to make the first term, n equals 1, the first term, it's actually going to make it become positive because the exponent is going to be even. So if we write it this way, it's going to cause the even ones to be negative. Okay. So these are called alternating series, and we know they're going to converge if all three of the following conditions are met. So all three of these things have to take place. Okay. A sub n is greater than 0. Each term of the series is positive. So that means all of these a sub n's right here, right, without the -1 part of it, the part that's making it negative, each of those has to be positive. Okay. A sub n plus 1 has to be less than or equal to a sub n for all n, or for all n greater than some integer. So if we go out and then it starts to do it, that's okay. All right, it's going to do it for some. Eventually the next term will be smaller than the previous term. That's what this is telling us, because this n plus 1 is the next term after this one. All right, so if we can show that the next term from some n value, integer value out, is going to be smaller than the previous one, then we can use this test. Okay, so we have to establish that. And then we also have to show that the limit as n approaches infinity of a sub n is equal to 0. Okay, this is going to be something that's coming up in the future. Okay, so this test is useful in checking convergence at an endpoint of an interval after the ratio test. Well, we haven't even taught the ratio test yet. All right, so that's actually the next test that I'm going to test or teach you after this alternating series test. Okay, but this is going to be helpful. This alternating series, it's going to be helpful for the endpoints of interval after we use this ratio test. And then we're going to be able to determine if what intervals these things are going to converge on. Okay, whether it's a closed interval or an open interval or half closed, half open. Okay, all right, let's go do a problem now. So we want to determine the convergence or divergence of this series. Okay, what I would always do is write out the first few terms of this series. Okay, so sigma n equals, and we're starting this one at 1. We're going to go to infinity of -1 to the n plus 1 power, and then 1/n. Okay, so if we start with 1, that's going to be a power of 2. That's going to make this positive, and we're going to have 1/1. The second term, that's going to make this power 3, because it's going to be 2 plus 1, which is 3. That's going to make this negative, so I'm going to write minus, and then 1/2. And then the third term we put in, that'd be 3 plus 1, that'd be 4. Okay, that's going to be +1. So this is definitely going to alternate, right? So this would be 1/1 minus 1/2 plus 1/3 minus 1/4, and then plus 1/5. And then the next one would be minus, and then dot, 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 because it's going to keep going. We need to write the 3 dots to show that's going to keep going. All right. So we kind of have an idea of what this is looking like. Okay. First of all, we know we're going to define, okay, so what's our A sub n? Our A sub n is the series without the negatives, okay? So it's going to be A sub n is equal to 1/n. All right, so what do we know about this? Well, one of the things we have to show is that this is always going to be positive, right? So, and we can just talk about this, okay? So if n is 1, 2, 3, 4, 5, 6, 7, 8, right? That's going to cause this to always be positive. So yes, the first thing is established, okay? A sub n is going to be greater than 0. It's always going to be positive. Okay. Now, the next thing we got to do is we got to establish that A sub n plus 1, and this is probably the hardest part of this, has to be less than or equal to the previous term. So the next term has to be smaller than the previous term, okay? So what would A sub n plus 1 be? Well, it'd be 1/n plus 1. So sometimes we can just put this in and see what happens, okay? So 1/n plus 1 is less than or equal to 1/n. So comparing these, okay, this denominator is going to be slightly larger than this denominator, causing this to always be smaller than this fraction. So that's true, right? And this is true for n greater than or equal to 1, okay? Which is what we have, right? We're starting n equals 1. Okay. Now, the next thing we got to show is number 3 is that the limit as n approaches infinity of A sub n, and that would happen to be equal to the limit as n approaches infinity of 1/n, because A sub n is 1/n, then what happens is n goes to infinity? Well, this gets closer and closer to 0. Okay, so we established that all the A sub n terms are positive, that the next term is, in this case, always going to be smaller than the previous term, okay? And then the limit as n approaches infinity of A sub n is equal to 0. So the terms are getting smaller and smaller and smaller, because that's why this is going to go to 0, okay? So each individual term is getting smaller and smaller and smaller, okay? So we've established those 3 things. Therefore, we know that this series converges. So we would say sigma n equals 1 to infinity of -1 to the n plus 1 power times 1/n converges by the alternating series test. Okay. And so that's the 3 things we have to show, that the A sub n is greater than 0, A sub n plus 1 is less than or equal to A sub n, and then the limit as n approaches infinity of A sub n is equal to 0. If we can establish those 3 things, then the series will converge. Okay. If we can't establish these 3 things, okay, then we're going to have to find some other way to show it either converges or diverges. Okay. So for this next example, we want to determine the convergence or divergence of this series. All right. And to use the alternating series test, what we need to do is always get it in the form of -1 times, or not -1 times, -1 raised to the some power, some n power, n or n plus 1. Okay. All right, so what I would do again is let's write out the first few terms of this series, okay? So sigma n equals 1 to infinity of n over -2 raised to the n minus 1 power. Okay, so if we put 1 in here, that's going to be 1 minus 1. This is going to be 0, okay? So -2 to the 0 power would be 1. And then the numerator will also be 1. So what we have is 1/1. And then if we put 2 in here, okay, so that's now going to cause this exponent to be a 1, right? And so -2 to the 1 is -2. And we put 2 in for n, that'd be 2. So but it's going to be minus, right? So this is going to be -2/2. And when we put 3 in, that's going to cause this to be positive, right? So this is going to be a 4 underneath, right? And what's it going to be on top? It's going to be a 3. So the numerators are always going to be the term number. So 1, 2, 3. The next one's going to be 4. Okay. And next after that's going to be 5 and 6 and so on. Okay. So that's a little bit easier. All right. If we realize that's happening. So let's do the fourth one, right? So if we put the fourth one here, 4 minus 1 is 3. So that's going to be -2 to the third power, which is -8. So it's going to make this minus 4/8. And then we're going to put the fifth term in, right? So that's going to make this 4. So that's going to make this 16. So 5/16, right? We're putting the fifth term in. So plus 5/16. And then the sixth term is going to be a 6 on top. But if we put 6 here, 6 minus 1 is 5. And so -2 to the fifth power would be -32. So this is going to be minus 6/32. And the next one you can see positive, negative, positive, negative, positive, negative, right? Next one's going to be positive and then ... Okay. So how do we get this? So because we need to rewrite it so it's -1 to a power so that we can find the a sub n term. Okay. So for this, we have sigma n equals 1 to infinity n over, and we can think of -2 as being -1 times 2. All right. So we can take -1 raised to the n minus 1 power and take 2 raised to the n minus 1 power. So -1 to the n minus 1 power. And then we have 2 to the n minus 1 power. So then, because this is just in the numerator and this is going to be -1, we could actually multiply it instead of divide by it. So that makes this n equals 1 to infinity of -1 to the n minus 1 power, and then times n over 2 to the n minus 1. And so right here, this is going to be our a sub n. Okay, so n over 2 to the n minus 1. This is going to be my a sub n. Okay, so I know that a sub n now is equal to n over 2 to the n minus 1 power. To use this alternating series test, I have to show that all of the terms are positive. Okay, so if we take a look at this, okay, n is equal to 1, 2, 3, 4, 5. Well, this numerator is always going to be positive. Okay, and this denominator is just going to be powers of 2. Once we put 1 in here, it's going to be 1 minus 1, which is 0. Then we put 2 in. This is going to be, so this is going to be 2 to the first power. Okay, and so this is just going to be wind up being powers of 2, which happen to all be positive, right? So what does that mean? That means a sub n, which is equal to n over 2 to the n minus 1, is always going to be greater than 0. Okay, so then the next thing we got to establish is that a sub n plus 1 is smaller than a sub n. Okay, and I should have said this. This is true for n greater than or equal to 1. Okay. All right, let me slide this up a little bit. Okay, so our second thing that we need to show is that a sub n plus 1 has to be less than or equal to a sub n, right? Okay, so what is that going to look like? What does a sub n plus 1 look like? It's going to be n plus 1. We're going to have to show that n plus 1 over 2 to the n plus 1 minus 1, which would really be 2 to the nth, is less than or equal to n over 2 to the n minus 1 power. Okay, so this is where some creativity comes in. All right, and what we're going to have to do is let me just do it with you and explain it. Okay, we need to use 1/2 is less than or equal to n over n plus 1. So this is my n right here. This denominator, or this numerator right here, becomes my denominator over here, and this denominator becomes my numerator. That's where I'm trying to get to. Okay, because if I can get that, then I can get to this. Okay, so there's a lot of ways we can write 1 over 2. All right, this is 2 to the 0 over 2 to the first power. 2 to the first power over 2 squared. So 1/2 could be 2 to the 0 power over 2 to the first power. It could also be 2 to the first power over 2 squared. It could also be written as 2 squared over 2 cubed, because both of these are going to cancel and a 2 is going to be left in the denominator, right? So another way of writing 1/2 is 2 to the n minus 1 over 2 to the n. That's just another way of writing 1/2. All right, so we have to realize that if we put this in the numerator here, all right, that's actually 1/2. That's where this 1/2 comes up, okay? So by establishing this, okay, n is 1/2 less than or equal to n over n plus 1? And the answer is yes, because, all right, so what if we have 1 here? Okay, so this would be 1 over 2. What if it was 2? This would be 2 over 3. Yeah, 1/2 is less than 2/3, right? 3. So this would be 3 over 4. 1/2 is less than 3/4. Okay. 4 over 5. Yeah. And so what's happening is this is getting closer and closer to being 1 as n gets bigger. Okay. So, 9/10, 11/12, 10/11. Okay. Kind of do that out of order. All right. 14/15, 19/20. Right? That's what this is. That's always going to be larger than this 1/2. Okay. And then we're going to allow, or not allow, but we can change this to this form of 1/2. So we have 2 to the n minus 1 power over 2 to the n is less than or equal to n over n plus 1. Okay. And then what we can do is multiply both sides of this by 2n and n plus 1. Now, why can we do that? Because this is not going to change. These are all positive values, and these are all positive values, so that will not change the direction of this inequality, right? It's going to stay the same. So if we multiply both sides by 2 to the n and also n plus 1, our 2 to the n's would cancel, and we would be left with n plus 1 times 2 to the n minus 1 is less than or equal to, and again, if we multiply both sides by 2 to the n and n plus 1, my n plus 1s would cancel on this side, and I'd be left with n times 2 to the n power. Okay, so I'm trying to get to this, all right? I'm trying to get to this, okay? So the next thing I could do is I could divide both sides by 2 to the n, right? Okay, or multiply both sides by 1 over 2 to the n. And so this would give me n plus 1 over times 2 to the n minus 1 over 2 to the n is less than or equal to, and this would be n. And then I can multiply both sides by 1 over 2 to the n minus 1, because these are also positive, right? And then we have n plus 1 over 2 to the n is less than or equal to n over 2 to the n minus 1 power. N minus 1 power, whoops. Okay, so what we've done by doing this is we've established that this is true, okay? So this is definitely true, all right? And then what's the other thing we need to do? Well, we need to show that the limit as n approaches infinity of a sub n is equal to 0, okay? So the third thing is the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity, and in this case, it'd be n over 2 to the n minus 1. Okay, and this is an exponential, and an exponential is always going to grow faster than, and this would be considered like a polynomial, okay? So, or a power function. This is always going to grow faster than this one, which means the denominator is growing faster, right? So it has a larger magnitude, which means this is going to approach 0, okay? All right, so we know that this limit is equal to 0. We know that the n plus 1 term is going to be less than or equal to the nth term, all right? And so we've established that this series is going to converge, all right? So now we know that sigma, let me slide this up a little bit, n equals 1 to infinity, n over -2, right? Because our original series was -2 raised to the n-1 power. Converges, because we've established these three things, by the alternating series test. And so that's how we know it converges, okay? All right, let's go to another problem. Okay, so for this next problem, we have sigma n equals 1 to infinity, -1 to the n+1 times n+1, all divided by n. Again, I would write out the first few terms. So sigma n equals 1 to infinity of -1 raised to the n+1 power. Because I think it helps us to see what's going on here. Okay, so basically this numerator is going to be one more than the denominator, right? And they're going to alternate signs. So if we put 1 in here, this is going to be a square, right? So -1 squared is going to be positive. So the first one we put in is going to be 2 over 1, and it's going to be positive. And then we put 2 in, that's going to be to the third power, which is going to cause it to be negative. So that's going to be minus. And if we put 2 in here, this is going to cause the numerator to be 3 and the denominator to be 2. So 3 over 2. And we should see really quickly that this is going to be positive, negative, and then positive. And this would be 4 over 3. And notice the denominator is the term number now, right? And then minus 5 over 4. And then plus 6 over 5. And then minus 7 over 6. And then plus ... Okay, it's just going to keep going. And we need the ... to show that it's going to keep going, okay? So this is this -1 to the n+1 is causing the alternating sign piece, right? So that means a sub n is the leftover part of it, which would be n+1 over n. Okay, so I've been going through and showing that a sub n is positive, okay? A sub n+1 is less than or equal to a sub n. And then we have to show that the limit as n approaches infinity of a sub n is equal to 0. Now, I've been doing those in that order, right? But you don't have to, okay? Especially when you see something funny is going to happen, right? So like this one, this numerator is growing, right? But it's always going to be larger than the denominator, right? So that's going to make these numbers be, they're going to get smaller, but they're always going to be, the numerator is always going to be bigger than the denominator, right? So if we go to do the limit, right, we know that this limit's going to, we should just realize, oh, this is going to come out to be 1 because this +1 is insignificant, okay? So we know that we're not going to meet these three conditions, right? So we can't use the alternating series test, but by default, we're going to have the convergence and divergence of this, okay? So for 1, we're going to go right to this limit statement, okay? So the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of n+1 over n, which is equivalent to finding the limit as n approaches infinity of n over n, and that would turn out to be 1, right? And it has to be 0 to use alternating series test. So we know we can't use alternating series test, but what's great about the alternating series test is if this limit doesn't exist, we actually know now that the series diverges, okay? So because the a sub n terms diverge, that means the whole series would have to diverge, okay, by the nth term test. So we could say sigma n equals 1 to infinity of -1 to the n+1 times n+1 over n diverges, okay, by the nth term test. So remember, if the limit does not come out to be 0, then the series would have to diverge, okay? So diverges by the nth term test. And we know it's going to diverge then, okay? So now we're going to look at something slightly different, okay? We're going to move into something different, and it's called the alternating series remainder, or the alternating series error-bound theorem, okay? All right, so for convergent alternating series, the partial sums we can use to approximate the actual sum of the series, okay? So, but how far are we off? Like if we do, the first 6 terms, how close are we compared to the actual sum? And this theorem will actually tell us how close we are, okay? So if a convergent alternating series satisfies the condition a sub n plus 1 is less than a sub n, okay, then the absolute value of the remainder r sub n. Now, what does that mean? That's the difference between the sum of the nth partial sum and the actual sum, okay? That's the difference between the two. That's called the remainder, okay? We know that remainder is going to be less than or equal to the first neglected term of the series, okay? So this S is actually the actual sum of the series. Okay, and this is the nth partial sum. This S sub n is the nth partial sum. And it's an approximation of the actual sum that we're calling S, okay? And so if we have the sum of the first 6 terms or 7 terms or something like that, then we know that the remainder has to be less than or equal to whatever the value of the next unused term is, okay? The next term. So if like a sub 6, then we would look at a sub 7. If we have the sum of the first 7, then we'd look at a sub 8. So the sub is 1 bigger than the sum we found, okay? All right? Okay, so let's do a problem involving this, okay? Now, for this series to even have a sum, it has to converge, right? That's what it means to converge, is it will have an actual sum, okay? All right, so if we take a look at, let's take a look at the first 6 terms on this, since we're finding the sum of the first 6 terms, right? So sigma n equals 1 to infinity of -1 raised to the n plus 1 power times, and it's 1 over n factorial. Okay, so if we put 1 in here, that's going to cause this to be positive, right? And it's going to be 1 over 1 factorial. If we put 2 in, that's going to cause this to be a 3, which is going to cause a negative, and it's going to be 1 over 2 factorial. And if you put a 3 in here, that's going to make this power 4, which is going to make it positive. So plus 1 over 3 factorial. And then minus 1 over 4 factorial. And then plus, and they're alternating, right? So plus 1 over 5 factorial. And then minus 1 over 6 factorial. And then plus ... Okay, so I'm just writing out the first 6 ones, okay? The first 6 terms. And so this is the same as 1 over 1 minus, and remember 2 factorial means 2 times 1. So this would be 1 over 2 times 1, which is 2. And then plus, and 3 factorial means 3 times 2 times 1. So it'd be 3 times 2, which is 6, times 1, which is 6. So this would be plus 1 over 6. And then minus 1 over 4 factorial is 4 times 3 times 2 times 1, which is 24. And then 5 factorial is 5 times 4 times 3 times 2 times 1. We have a factorial button on our calculator too, okay? So this would be 1 over 120. So they start getting large fast, right? And then minus, and the final one would be 6 factorial, turns out to be 720. Okay, so let me show you, how I've done these a lot, so I know how to do it, all right? But if you want to know how to find 6 factorial, you can just press 6 on your calculator, and then you press alpha, and then window, and come down here to number 9, and that will give you 6 factorial, which is 720. Okay. All right, and then this should be plus, and then ... because it does continue. All right. Okay, so we know that a sub n is going to be this 1 over n factorial. Okay, so 1 over 1 factorial, all the denominators, when I take the factorial, they're all going to be positive, right? And the numerator is going to be positive. So yeah, a sub n is going to be greater than 0 because a sub n is equal to 1 over n factorial, right? And then I'm going to do the limit right now. Okay, so what is the limit? So the limit as n approaches infinity of a sub n, which would be the limit as n approaches infinity of 1 over n factorial. Well, this numerator is always going to be 1, right? And this factorial causes the denominator to grow, right? So this overall is going to get closer and closer to 0, right? And then the third thing we need to establish is that the a sub n plus 1 is less than or equal to a sub n, right? Okay, so what if we just put n plus 1 in, right? If we put n plus 1, we'd have 1 over n plus 1 in parentheses factorial, and that'd be less than or equal to 1 over n factorial. Well, this is going to be large. N plus 1 is going to be larger than n. So we don't have to do anything like the 1/2 like we did last time, okay? We don't have to do anything fancy like that, okay? Because here we go. If we put n plus 1 in, right, this denominator is bigger than this denominator, right? And factorial is going to make it even more larger, right? So this denominator with the factorial is going to always be larger than this one, which makes the overall fraction smaller than this fraction, okay? All right. So what do we know? Well, we know the limit is equal to 0 as n approaches infinity. We know we have positive terms, and we know the n plus 1 term is always going to be less than or equal to the nth term, right? And this is for n greater than or equal to 1, and this one's for n greater than or equal to 1 also. Okay, so we know it converges, which means it has a sum, right? We don't know what the sum is, right? It's not like the geometric series where we can actually figure out the sum, but this is going to have, this actually has a sum, okay? Okay, so what we know is that sigma n equals 1 to infinity of -1 raised to the n plus 1 power times 1 over n factorial converges by the alternating series test. Okay, so we know it converges. All right, so now we don't know what the sum is, right? But we know we're going to take, I want to know approximate the sum of the series, of the following series by its first 6 terms, right? So that's going to be S minus, since this is the first term, right? Second term, third term, fourth term, fifth term, sixth term. This is going to be minus S sub 6. So the absolute value of that, which we know we're calling the difference between those is the 6th remainder, right? And we know that that's going to be less than or equal to the next unused term, right? So that would be the a sub 7. Okay, and a sub 7 is 1 over 7 factorial. And 7 factorial, that's a big number. It's 1 over 5,040. Okay, and then if we want to find the 6 terms, okay, one way we could do it is we just take 1 minus 1/2 plus 1/6 minus 1/24 plus 1 over 120 minus 1 over 720. You could do that, put that into your calculator and see what you get for that, okay? Or you could also do this, okay? So I'm going to do it actually with the summation notation, okay? So alpha window and then number 2. And then we're going to do n, because I'm in if you check, I'm still in the sequence mode, okay? So if you're in sequence mode, it's going to give you an n. You could do this with x also, okay? So n equals 1, and we're only going to go 6, right? And then the series is going to be, and then -1 raised to the n plus 1 power, then come out of the power, and then parenthesis, and then a fraction, and then 1 over n, and we need the factorial, right? So we press alpha window and then select number 9 for the factorial. Okay, and then close the parenthesis for that. This last parenthesis is the ending for the summation, And if we press enter, we get this decimal, right? Which, if we want to switch to a fraction, because it would be a fraction because we have 6 fractions here, right? It would be 91 over 144. So how I got that is I went to math and then selected my answer, number 1, which was changed to a fraction, okay? So 91 over 144. So I know my 6th term is equal to 91 over 144. Now, the decimal approximation for that was 0.63194. Okay, so this is the sum of the first 6 terms, right? All right, so here we go. All right, this S of 6 is really 91 over 144. So I know the absolute value of S minus 91 over 144 is less than or equal to my 7th term, which would be 1 over 5,040. Okay, now this is an absolute value inequality, and how you solve it is that the absolute value, right? That's how far you are from 0, okay, on the number line. That distance has to be less than this. Well, that means it's in between. So here's a formula for this. If you have something like this, x minus a is less than or equal to some r, then that means x minus a has to be in between negative r and r. And I wouldn't need the absolute value, sorry. I put the absolute value in there by accident. All right, so what that means is that this is somewhere between negative 1 over 5,040 and positive 1 over 5,040. So we could write this, negative 1 over 5,040 is less than or equal to S minus 91 over 144, which is less than or equal to 1 over 5,040, which means I can get the sum by itself by adding the 91 over 144 to the left, the middle, and the right. So this would be 91 over 144 minus 1 over 5,040 is less than or equal to my sum S, which is less than or equal to, and then I would add 91 over 144 to the 1 over 5,040. Okay, so if I put this into my calculator, okay, let me slide it up a little bit. Okay, so if I put this into my calculator, I get a decimal approximation of 0.63, I'm going to go a few decimals out, 63175 is less than or equal to my sum, which is less than or equal to, and if you put this into your calculator, you get a decimal approximation of 0.63214. So what this means is our sum is in between these two values. Okay, so that's how we can get this approximation and know how close we are. Like 0.63, 0.63, right? So we're only the 3rd decimal place off. That's the difference between these, right? So we are really tight in how close we are to the actual sum of this, right? And the more terms you go out, the better the approximation is going to be, right? Okay. All right. So and this still doesn't tell us the sum. It just tells us, okay, this sum is going to be somewhere in between these two values. Okay. All right, let's go to the next thing. So now we're going to move it on to something different, okay, even than that. And it's called the absolute and conditional convergence. All right. And what happens is sometimes we have series, they're dealing with positive and negative terms, but they're not alternating. Like you might have a first 3 are positive and the next 5 are negative, and then the next 4 are positive and the next 2 are negative. Like it could happen like that. All right. So how do you determine the convergence of that? Okay. So one way is to start looking at the series, the absolute value of your a sub n term. Okay, so the whole thing, which is going to cause the terms to all be positive, right? Okay, so what we have to do is we have to look at this one, and we're going to take a look at, okay, what is the series with the absolute value in it, right? Okay, so we're going to use direct comparison on this. All right, so this is, hear me out for a little bit, okay? So we know that sine of n is somewhere between -1 and 1, which means, by what I just talked about just a minute ago on the last problem, right? That's the absolute value of sine of n would have to be less than or equal to 1 for all n, right? Because I know sine fluctuates between -1 and 1. The absolute value of it would always have to be less than 1. It's going to be somewhere between 0 and 1, okay? Which is the absolute value. All right. Now, what if we divide this by n squared, right? And we get this, right? Or absolute value of n squared, right? Okay, so this numerator is going to be smaller than this numerator, right? And the absolute value of n squared, well, n squared is going to be positive, right? So we really don't need the absolute value on this bottom, but we do for this to make it match this, okay? But these denominators are going to be the same, but the numerator is going to be smaller, right? So what does that mean? Okay, so 1 over n squared, we know that series converges by the p series, right? 1 over n squared converges because our power is 2, right? It's bigger than 1, which means this one converges. And this one is bigger than this one, right? We're showing that right here, okay? Then, and this one converges, which makes this one converge, okay? So we know that this new series with the absolute value of sine n over n squared, we know that it's gonna converge, okay? And it converges by this direct comparison test, okay? So what we know is this, okay? And this is a theorem that's been proven, okay? Is that this, if the series sigma n equals 1 to infinity of the absolute value of a sub n converges, then the series must converge. So we just proved that the absolute value one converges, right? And so using this theorem, now we know back up here, n equals 1 to infinity, sine n over n squared, oh, that one's going to have to converge also by this theorem, okay? So if the absolute value one converges, then the basic one converges too, okay? So that's a way in which we can show that something that has positive, negative terms, but they're not alternating, we can show that it's actually, in fact, going to converge, okay? All right. All right, let's go down to the bottom because there's a little part down here that I want to talk about. So I want to say this, okay, this is going to be really important. If the absolute value one converges, then the series a sub n converges, right? But the converse of that, which means if this one converges, that doesn't make this one converge, okay? So a perfect example of that is, let's say this is our series, right? Our a sub n is -1 to the n plus 1 over n. And so this is 1 over 1, 1 over 2, 1 over 3, 1 over 4, but they're alternating, right? Turns out that this one is converging by the alternating series test. We could prove that and go through it, okay? Because a sub n would equal 1 over n, right? And we would know that the limit as n goes to infinity of 1 over n is equal to 0. We know that a sub n is greater than 0, right? And then we would also know that a sub n plus 1 is less than or equal to a sub n, which would be 1 over n plus 1 would be less than or equal to 1 over n, right? So, all right, so this series right here would converge, right, by the alternating series test. That's what these three statements are, right here, and right here. We know these three statements are true. Okay, so this series that's -1 to the n plus 1 over n, right? It's going to have to converge by the alternating series test. All right. But we should also realize that the absolute value of this would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, 1 over n, right? It would just be 1 over n. We should recognize that that one actually diverges, right? Because that's the harmonic series test, and we can, or harmonic series, and we know our p-value is 1, which means it has to diverge, right? So you could use, we know that the harmonic series diverges, or you could use the p-series test to show that 1 over n, okay, the positive, the absolute value of these, that each term, that we know that the absolute value one would actually diverge, okay? So the series converges, but that doesn't mean that this one converges. So here's a perfect example, is this one converges, this one diverges, Okay, if we take the absolute value of it, because it'd be the harmonic series. Okay, when that happens, when the actual series converges, but the absolute value of the nth terms, if they diverge, then we say that's conditional, conditionally converges. Sorry, couldn't think of the word. All right, or conditionally convergent. Okay, so let's flip the page and let's go to the next one. So I want to write these two statements. This is the definition of absolute and conditional convergence. Okay, I always like if statements to be the first one. Okay, so this is coming at the end. You could write it either way, but I like to say, look at it like this. Okay, so if n equals 1 to infinity, the absolute value of a sub n converges. Okay, that tells us, so arrow, right? So the conclusion we can make from that, if we have this, we would say that the series a sub n would converge.
Evelyn Camarillo, please report to the front office. Evelyn Camarillo, report to the front office.
And then this one says, if this one converges, but the absolute value one diverges, then we would say it's conditionally convergent, okay? All right. And if they both diverge, then it's just divergent, okay? We don't have that, all right? So if this one, if sigma n equals 1 to infinity, absolute value of a sub n diverges, and the actual series 1 to infinity a sub n converges, then we say we can make this conclusion that this sigma n equals 1 to infinity a sub n is conditionally convergent. Okay, so next what I want to do is look at some of these problems and determine if it converges or diverges, and then classify it as either absolutely convergent or conditionally convergent. Okay, so absolutely, you can think of this. Absolutely convergent is if the absolute value converges, we know the series converges. Okay, but that doesn't necessarily mean if the absolute value of it diverges, then a sub n could still converge. Okay, all right, so the absolute value of the series doesn't necessarily mean the series will actually do the same thing. Okay. All right. Okay. So let's take a look at this next problem. All right. So if we take a look at, let's take a look at, this is an alternating series, right? Positive, negative, positive, negative. So we could start with the alternating series test. So our a sub n would be equal to n factorial over 2 to the n. And okay, I know factorials grow faster than anything else. So I know right now that this numerator is growing faster than this denominator, okay? So factorials grow faster than exponentials, all right? So now what I know is that the limit, as I'm gonna go right to the limit statement, the limit as n approaches infinity of n factorial over 2 to the n. Well, the numerator is growing faster, so I know this is gonna come out to be infinity. Okay, so it's not coming out to be 0, so we can't even use the alternating series test, right? And because that's not coming out to be 0, we can also say, oh, that's gonna be diverging, right? So we automatically know that this series, sigma, n equals 1 to infinity of -1 to the n power times n factorial over 2 to the n, we know it's gonna diverge by the nth term test. So that nth term test is always a good test to show that something diverges. Okay, so right off the get-go, okay, so whenever on the alternating series test, whenever we get something that's not equal to 0, we know the actual series is going to diverge every single time. Okay, all right, or I wrote nth term diverges. Okay, diverges by the nth term test, not diverges. Okay. All right, and that's all you'd have to write up for this. Okay, let's go to the next problem. Okay, so this next one, I want to determine whether each of these series is convergent or divergent and classify it. Okay, is it divergent, or is it absolutely convergent, or conditionally divergent or convergent? Because there's three of those. Okay. All right, so let's take a look at, here's our series. I wrote out the first few terms for us. Okay, let's take a look and see, what does this series, if we take the absolute value of it, become? Okay, so if we take the absolute value of -1 to the n power over the square root of n, okay, so this is going to cause it to be alternating signs, right? Negative, positive, negative, positive. Okay, what I know is if I take the absolute value of it, we can get rid of that, right? That's just going to become 1. So n, or sigma, n equals 1 to infinity. This becomes just 1 over the square root of n. Well, square root of n is really n to the 1/2 power, right? So that's sigma n equals 1 to infinity of 1 over n to the 1/2 power, right? And so what do we know? We know P is 1/2. This is a P series test, right? P equals 1/2. And for it to converge, it would have to be bigger than 1, right? So P is equal to 1/2, and 0 is less than P is less than 1, okay? Which tells us that this series diverges. So sigma n equals 1 to infinity, the absolute value of -1 to the n. That's the series we're talking about here. Square root of n diverges by the P series test. Okay, so right off the get-go, we know it's not absolutely convergent, right? Because if this was convergent, right, then we would know the actual series is also convergent and we wouldn't have to do any more tests. Okay, so it's a quick and easy way, right? So that's why we want to start with the absolute value one. Okay, all right. So this could be conditionally, if we take this original series that we started with, it could be conditionally convergent if we can show that this series converges, and this is an alternating series. So we could use the alternating series test to see if this series converges, okay? All right, so let's take a look at this one. This would be sigma n equals 1 to infinity of -1 to the n power times 1 over the square root of n, right? Okay, so how do we show the alternating series test, whether it converges or not, right? This is going to be our a sub n. So we know our a sub n for this test is going to be equal to 1 over n to the 1/2, right? Or the square root of n. All right, so what if I do the first one? Okay, so the first one is, let's show that a sub n is greater than 0. Okay, so that would be 1 over the square root of n would have to be greater than 0. And that would be true, right? That's true for n greater than or equal to 1. Because if you put 1 in here, right, square root of 1, square root of 2, square root of 3, square root of 4, those are all going to be positive values. Yeah, so this is true, okay? How about the next one? We got to also establish that a sub n plus 1 is less than or equal to a sub n. So this is a quick one that's easy to show, right? We just got to put n plus 1 in, right? So 1 over the square root of n plus 1 would be less than or equal to 1 over the square root of n, because this denominator is bigger than this denominator. We know the square root function is increasing. So if we do n plus 1, that's going to have to be bigger than this one. Okay. Since this denominator is bigger than this one, this overall fraction is going to be smaller than this fraction. Okay. Always. So this is also true for n greater than or equal to 1. That's going to be true. All right. And then we just need to do the limit. So the third thing is, okay, so what's the limit as n approaches infinity of 1 over the square root of n, right? A sub n, which is 1 over the square root of n. Well, as this gets bigger and bigger and bigger, yeah, that's going to get closer and closer to 0. So what does that mean? Okay, this series, the actual series that we started with actually converges. The absolute value of the terms of the series don't, right? That series doesn't. But the actual series that we were looking at, it does converge, right? By the alternating series test. So we could say sigma n equals 1 to infinity of -1 to the n power over the square root of n. We know that that converges by the alternating series test. Okay, now, again, the series we started with, right? The sigma n equals 1 to infinity of -1 to the n over the square root of n, that one's converging, right? When we took the absolute value of it, that one was diverging. So when that happens, this is called conditionally convergent. So we would classify this as sigma n equals 1 to infinity of -1 to the n over the square root of n is conditionally convergent. So let me go back. If we had established up here, like let's say this is -1 to the n power over into the fifth power or something like that, right? Then we would have known by the P series test that it actually converges, right? And we wouldn't have had to go any further because if the absolute value converges, the actual series would also converge and we'd be done, right? We wouldn't have done this extra step. That's why it's good to start with, okay, let's start with the absolute value and see what happens, okay? You want to do this when you have terms of the series that are negative, okay? All right. So for this next one, we have n equals 1 to infinity, -1 raised to this ugly power, right? N times n plus 1 over 2, 3 to the n. Okay, so this -1 to these different powers, right? That's going to cause it to be negative, and this one's negative, negative, and then positive, and then positive. So this is a perfect example where we couldn't even use the alternating series test, right? So what does this become, right? If we take the absolute value, let's take a look at, this is the only way to do this problem is to look at, okay, what happens when we take the absolute value of it? So n equals 1 to infinity of the absolute value of -1 raised to the n times n plus 1 over 2 over 3 to the n power. Okay, so what that's going to do is all of these terms, 1/3, 1/9, 1/27, right? They're all going to be positive. So this would be 1/3 plus 1/9 plus 1/27 plus 1 over 81 and then plus ... right? Okay, so we should pick up on a pattern here, right? So this, the absolute value of this one, right? It's 1/3, 1/9. So we're multiplying this one to go this one, multiplying by 1 over 3. From here to here, 1 over 3. From here to here, 1 over 3, right? So we could rewrite this as sigma n equals 1 to infinity of 1/3 raised to the n power. And what do we know about this? Well, this is a geometric series, right? And because r equals 1/3, and because we know that 1/3 is between -1 and 1, we know that sigma n equals 1 to infinity of the absolute value of -1 raised to the n times n plus 1 divided by 2 power over 3 to the n converges by the geometric. We actually probably should capitalize this because it's the name of something, right? Geometric series test. R is less than 1. Absolute value of R. Whoops. Absolute value of R is less than 1. Okay, so we know it's going to converge if the absolute value of R is less than 1 by the geometric series test. Okay. All right. So what does that mean? Well, the absolute value of this converges, which means this one also must converge by the absolute value convergence theorem. So now because that one converges, now we know that sigma n equals 1 to infinity of -1 raised to the n times n plus 1 divided by 2 over 3 to the n power converges by the absolute value convergence theorem. That theorem says that that one's going to converge, okay? All right, so what do we know about this? How do we classify it? Well, this is called absolutely convergent, okay? So this series, sigma n equals 1 to infinity of -1 raised to the n times n plus 1 divided by 2 all over 3 to the n is absolutely convergent. All right, and that's how we classify it. All right, that's it for that problem. Let's go to another one. All right, for this next problem, we have this series. I've written out the first few terms. If you notice, okay, they are alternating, right? Okay, but let's take a look at what happens if we look at the absolute value of it, right? So let's take a look at sigma, because we'd be done. If we knew this converges, we'd be done. Okay, so sigma n equals 1 to infinity of the absolute value of -1 to the n over ln of n plus 1. Okay, so what would happen with that one? Well, that means this -1 wouldn't be there, right? So this becomes sigma n equals 1 to infinity of just 1 over ln of n plus 1. So that'd be 1 over ln of 2 plus 1 over ln of 3 plus 1 over ln of 4 plus, and then ... right? It would keep going. 1 over ln of 5, 1 over ln of 6. All right. Okay, so this series, right? One like this, like what are some tests that we've gone over, right? So if a sub n is something that is easily integrable, okay, that we can integrate it, then we might want to look at the integral test. And in this case, that's what we want to look at, okay? So we're going to let f of x equal 1 over ln of x plus 1, okay? Now, to use the integral test, right, we have to show three things, right? We have to show it's continuous, we have to show that it's positive, and we have to show that it's decreasing, okay? For in this case, for x greater than or equal to 1, okay? All right, so right off the get-go, what we need to do is rewrite this, okay, as ln of x plus 1 raised to the -1 power. Okay, that's going to allow us to find the derivative, because that's the part that's going to be the most difficult. Like we have to show that that the derivative is always going to be negative, because that would mean it's decreasing. All right, so f prime of x is equal to -1 times ln of x plus 1, and then multiply that and then subtract 2. Okay, and then multiply that by the derivative ln of x plus 1, which would be 1 over x plus 1. Okay, so this would be -1 on top, and then times, this would be, or just -1 on top. Let's just do that. -1 times, and this would be 1 over ln of x plus 1 squared times 1 over x plus 1, right? So this becomes -1 over x plus 1 times ln of x plus 1 squared. Okay, so this is for x is greater than or equal to 1, because n is equal to 1, right? So x greater than or equal to 1. If x is greater than or equal to 1, right, this is always going to be positive. Natural log of this is always going to be positive, right? And we take ln of a positive value, we're going to get a positive value. For bigger than 1, we're going to get positive values, right? When we take the natural log of 1, it's 0. Anything bigger than the natural log of 1, which we'd be taking the natural log of 2 right here, right? So that would be positive. And even if it turned out to be negative, we're squaring it, right? So which is going to make it positive. So what does that mean? The denominator is always going to be positive. The numerator is always going to be negative. That means this derivative is always negative for x greater than or equal to 1. That means it's decreasing, okay? So what do we know about this? This is always positive, right? We know it's going to continuous because we're putting 1, 2, 3, right? The only thing that would cause it to not be continuous is if this was less than 0, okay, or 0, but we're not putting those x values in, right? So we could say f of x is continuous. And order necessarily wouldn't matter here, but we have to show it's continuous, positive, and decreasing for x greater than or equal to 1. That's true, right? Which means we can use the integral test. Okay, so now what we're going to do is we're going to take the integral and we're going to start it at 1 and go to infinity of our function, which is 1 over ln of x plus 1 dx. Okay, so here I'm not going to actually do the integration, okay? So if we worked it out, okay, so equals and then dot, 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 right? This integral would turn out to be infinity. Okay, so what does that mean? Remember the integral test says, okay, whatever the integral does, the same as this, the series will do the same thing, okay? So what does that mean? That means this absolute value of this series, right? This is what we got up here. That means since the integral is diverging, the series will diverge by the integral test. Okay, so that means sigma n equals 1 to infinity of the absolute value of -1 to the n over ln of n plus 1 diverges by the integral test. Okay, so if you're doing homework on this, you actually have to work out the integral, okay? I'm just doing that to save some time here because we've practiced that a lot, okay? All right, so now so we know it's not absolutely convergent, but it could still be conditionally convergent, and that is, does this original one actually converge, right? So now we have to go back to this, right? And so now we're going to take a look at rewriting this as n equals 1 to infinity of -1 to the n times 1 over ln of n plus 1, right? And so now we're looking at the original series, this one up here. I just made my -1, I'm multiplying by -1, okay? Because that means this, I'm going to make this be my a sub n. Okay, so a sub n is equal to 1 over ln of n plus 1. And to use the alternating series test, I have to show that the limit as n approaches infinity of this is 0. I would actually probably start with that because that will tell you everything right at the get-go, right? Because if that one doesn't, if it doesn't turn out to be equal to 0, okay, then automatically that means it's going to diverge, right? And so both the series and the absolute value of the series is going to diverge, okay? So the limit as n approaches infinity of a sub n, which is the same as the limit as n approaches infinity of 1 over ln of n plus 1. Well, we know the natural logarithm function keeps increasing, right? It's always increasing. So that means this denominator is getting bigger and bigger and bigger. It's going to infinity, right? And if that's going to infinity, that's going to make this overall fraction get closer and closer to being 0. Okay, so we know the limit's 0, right? All right. What about the terms? Well, for n greater than or equal to 1, right? Then we know that this is going to be natural log of 2, natural log of 3. Those are all positive values because the natural logarithm is always greater than 0 or positive for n or for inputs greater than 1. Okay, so we now have a sub n is greater than 0, which means 1 over ln of n plus 1. That's going to have to be greater than 0 because I should say this, for n greater than or equal to 1. That's going to be true because we're taking the natural log of 2, then the natural log of 3, then the natural log of 4, natural log of 5. Those are all going to be positive values down here, okay? And then the last thing we got to establish is that the next term is smaller than or equal to the previous term, okay? So for this one, right, really all we're going to have to do is put n plus 1 in here, because that's going to make this, if we put n plus 1 in right here, that's going to make this n plus 2. We're putting a larger input into the natural logarithm function, which means it's going to be bigger. This denominator, when I put n plus 1 in, is going to be bigger than this one, this original one. So we have to establish that a sub n plus 1 is less than or equal to a sub n. So that would be 1 over the natural log of, this becomes n plus 1 or n plus 2 is less than or equal to, and let me slide it up a little bit so you can see it, 1 over ln of n plus 1. This is a bigger input for the ln function, right? For the natural logarithm function, which means this denominator is going to be larger than this denominator, which makes this fraction smaller than this fraction, okay? So this is true for n greater than or equal to 1. So we've met the 3 conditions, right, for the alternating series test. What does that mean? That means the series sigma n equals 1 to infinity of negative 1 to the n over ln of n plus 1 converges by the alternating series test. Okay, so the absolute value of a sub n up here, the original, right, that we tried, the first thing we tried up here, right, didn't work. It diverged, right? But the actual series converges, right? So we now know that the series is conditionally convergent. So how we classify this is n equals 1 to infinity, negative 1 to the n over ln of n plus 1 is conditionally convergent. So if the absolute value, and I didn't do an example like this, if the absolute value one, let me zoom out a little bit. Okay, that's a lot of work. These are a lot of work. I'm telling you that right now. Okay. If this one diverges, right, that's what we had up here. This one could also diverge, right? And automatically that just means it's divergent. Okay, there's no classification for that. It just diverges. All right. Okay. So if the absolute value one converges, then we know the original one converges, right? And then if the absolute one diverges, but the original one converges, then it's conditionally convergent. Okay. All right. And that's it, right? That's the alternating series test. Okay. And we're going to work more on this tomorrow. So I'll have another video tomorrow on just alternating, another day on alternating series, because this takes a little bit of time to get the hang of. Okay. All right, guys, that's it for today.